Welcome everyone, my name is Angel Francisco Martinez. I am dubbing this presentation for Dr. Javier Moreno from SEDEX Spain. And the session today will cover how to export complex 3D meshes from Midas GTS NX to Flac3D, as well as a one-to-one comparison between the two platforms for various examples. The Dr. Moreno will be joining us at the end of the session to answer questions live. And so feel free to answer all your or ask your questions along the session. This will be the content of today's webinar. We'll be briefly covering the learning objectives, and then we'll do a comparison between the two software, Midas GTS NX, which is a FEM or finite element method approach, and Flac3D, which is FDM or finite difference method approach. So we'll cover the key differences and similarities. And then we'll jump into the structure of the import file, which is the impgrid, which allows basically the program to it's a command in Flac3D that allows it to read text files that have information about nodes, hence allowing the possibility to bring information in from Midas. We'll also look into the fish subroutine that is used to extract the information from the files created in Midas in order for them to be able to be imported by impgrid into Flac. And then we'll cover two examples. One is a stress deformation of a bridge pier. Again, model in Midas, and then run to completion in Midas, but as well as being exported to Flac and then run in Flac, and we'll compare the results. And we'll do the same for a seepage analysis, and finally look into the conclusions. So starting with the learning objectives, the goal for today is to show a one-to-one comparison for notable results between the programs Midas GTS NX and Flac3D on the two project applications. But as we're going to be going through those one-to-one comparisons, the session will also cover the following key points, which is how these meshes, these volumetric meshes, are generated in Midas GTS NX and then exported to Flac. And then I'll also review the conceptual differences, the main differences between the two methods, the FEM and the FDM, as well as break down the fish subroutine used for importing the mesh into Flac. And as we're going through this process, as I mentioned, there will be two examples that will be used to show the execution of this import, like the mesh being imported, as well as running the analysis to show the notable results and compare them. Now, just to point out that this is not a comparison as to which software is better, as both have their high merit. And what we really would just want to focus is that these two softwares do have a link between them that can be shared. So jumping into the I guess between the two programs, Midas GTS NX and Flac3D. The first is just to cover what would be basically the overlying similarities between the two. First with Flac, just to point out that this is a software formulated under the finite difference method, whereas Midas GTS NX was formulated under the finite element method. However, both are numerical methods used to solve geotechnical problems. To solve the problem, both will subdivide a large or whole domain of a large problem into smaller, simpler parts. And in Midas, they're called elements, whereas in Flac they're called zones. Then simple equations are used to model these smaller elements or zones, and then all these then subsequent equations are assembled into a larger equation system that's going to model the physics of the entire problem. And then this system will describe the physics mathematically through partial differential equations. And how they solve these partial differential equations is what we're going to be covering from here on out, like what makes the big difference in the programs. But the last point and the most important point is that there is a connection between the two methods, that certain formulations of finite element method defined, following certain sort of rules or regular grids can be equivalent to those of the finite difference method, and hence it's possible to link them up. I'll go one by one. So first off, on the left for Flac, it's not typical to use it for, let's say, irregular geometries in 3D. Mostly it's defined as rectangular or block shapes on regular grid. And so it's hard to use CAD files or CAD geometries. Whereas with Midas GTS NX, it's very much able to import or generate, or more importantly, mesh complex CAD. And so it makes it very advantageous for the shapes or problems that require more accuracy in the geometry or more details. Going back to Flag, the in terms of now solving the partial differential equations, it's the most direct approach, and hence it doesn't need to assemble a stiffness matrix to solve this. Whereas the Midas GTS NX does need to assemble a stiffness matrix, and the calculation hence can be stopped by a singularity in this matrix. In Flag, all calculations can be considered dynamic. What we mean by that is that it uses the same algorithm to solve for static problems as it does for dynamic, and the calculation is explicit. So basically, you need to set up very small time steps, very small order magnitudes, in order for the program to be able to solve the problem. In Midas GTS, however, there are different calculation algorithms for static or dynamic. It can run both. And calculations for dynamic analysis can be carried out both in the explicit and the implicit schemes. A few more differences for Flag. The static analysis, the software will over-dampen the material to avoid parasitic oscillations. So basically, it's treating the static analysis as a dynamic analysis with very, very small time steps. Whereas, as we said, Midas GTS NX can run static, dynamic, as well as eigenvalue analysis in order to obtain frequencies or vibration modes. In Flag, the time does not have a temporal concept. Rather, as we've been saying, they're considered small enough time steps for the energy that's being applied or the forces being applied to be able to diffuse throughout the model in small enough increments in order to simulate the, I guess, problem as they're trying to do either static or dynamic. Whereas in GTS NX, the dynamic analysis can be either carried out in the time or frequency domain. Flag can only carry out the dynamic analysis in the time domain. And another big difference, however, for the two is that computational time for Flag is actually going to be the same regardless of whether the problem is behaving in an elastic or linear or elastoplastic nonlinear behavior. Whereas with Midas GTS NX, by the computation time for the linear analysis is actually much lower, much faster to run a static or an analysis under the linear behavior than something that has to be run with that nonlinear or elastoplastic behavior. More notable differences would actually be now jumping into how to use the softwares themselves. So on the left, the Flag interface is all the commands, all the inputs, everything is done through command files. There's a Fish programming language for this that you can write the subroutines and then use, all these different subroutines to the more advanced models or have multiple uses of these fish subroutines to create everything from defining materials to executing the analysis to defining the equations that will be used. And so here's a screenshot of what Flac3D looks like for one of the examples that we're using today, this being the fish code. Whereas on the right side with Midas GTS NX, the interface is more of a graphical interface. It's very friendly. All the input commands are even geometry or materials or everything is done directly as we see here on the screen by icon codes or click, input clicks, and it's no code required. However, that does mean that Flag is more, yes, versatile for people who have experience enough to be able to, to develop that ability to get to a level of coding. You can basically have more freedom to do or model anything you want. Whereas with Midas, that there's no input or there's nothing to modify in terms of the source code. It's all locked, and so it's all about the icon interface commands. In particular, for the main reason why we're showing the sessions is the connection between the two is where their differences start to become more apparent and is in the geometry or in the types of meshing. So for Flac3D, there any kind of 3D mesh has to come from one of these 13 primitive geometries. So it has to have a combination of one of these shapes to eventually get your full model. Whereas with Midas GTS NX, you can mesh any solid, any volume that you like, and you can create this by either importing from CAD programs. We see here a list of the formats that the program can import. So all the main AutoCAD files, 3D can be brought into Midas for meshing. However, we also have the commands like you would on like an AutoCAD program for generating your geometries from scratch as well. So you see here a screenshot of the geometry commands. You can draw on grids or as well as solids, and then once you have them as well, any kind of modifications, just like you would on any AutoCAD program. So that's really where the advantage for 3D starts to be more notable for people who use GTS NX, is they can really approximate their problem a lot more accurately into what is happening physically relative to the effort it would take to do something like that based on a set constricted rules of geometries. This is just a little clearer picture of what these shapes look like, and they have to basically is restricted to be within these specific norms. But also note that this image points out the location of what are these nodes or corners, and there's a certain sequence to them. So that also has to be, as we will see later in the import format, taken into consideration. What's the order of these nodes going to be arranged in order for the import to be properly conducted? And so getting now into those details of how these two programs are able to share meshes information between each other. During meshing for FLAC, the volume is divided into what we would call, or what they refer to as zones, and they each have a grid point at the corners. So we see here, this would be like a one zone that has grid points, 8 grid points in this sequence. Similarly for like a wedge. They do point out that there are no grid points in between or as midpoints. We see here that between 1 and 2 there is no division, like there might be something we see here on the right side for Midas. So that's basically another way of saying that it's like they're not higher order elements or second order elements. Whereas with Midas, when we divide a volume, we refer to them as an element. It's made up of elements, and each element has nodes. This would be one element that has corner nodes, and they also have, I mean, if it's a linear element, the nodes are only on the vertex at the corners. However, we can also do second order elements which have nodes in between the nodes, as we see here in these images. So that's one thing to consider, that we can import linear elements into FLAC, but we cannot import second order elements into FLAC because FLAC just doesn't know or doesn't formulate their zones with that setup. So here's a little bit more kind of clarification. What we refer to nodes in Midas are grid points in FLAC, as well as what we refer to elements in Midas, we refer to zones in FLAC. And here we're showing the second order elements for Midas, whereas that's not possible in FLAC. Okay, so now that we've covered the comparison between the two, similarity and differences, we can jump into the structure of what's going to be the file being imported or read by FLAC with the information of the mesh generated in Midas, and that is called the impgrid. So the structure for the import commands are as follows. Basically that's impgrid is a specific command by FLAC to import generate volumetric meshes. So that means that they can use this for not just importing meshes from Midas, but from any other software that generates 3D meshes, and that's how they do it using this command. This is the format, so you basically call impgrid and then the file name with the keywords, and the file name will have an extension limited as Flac.3D, and then the keywords have information about the IDs that would identify the grid points or the elements, the nodes and the zones that are indicated in this import file, this Flac3D. And so what this does is now the command will be then reading this information about the grid points and generating them in Flac, and so it's therefore able to now import meshes, incorporating them even into already existing meshes. And so the file name itself has some rules, which for it to work, it has to be in the American Standard Code of Information Interchange. You know, comments in the file are marked by the asterisk. And then if we were to look into this file, this would be some of the information. We'll open one just as an example in the next slide. But this would be information that you would see along the lines, and you see a word related to or a code related to G that indicates a grid point, and this must be followed by an identifier, basically grid point number 1 or grid point number 10, and then its coordinate location XYZ. If you see a line with the C, it indicates that's a zone, and it must also have an ID identifying it, as well as what type of zone it is and the information about the grid points it's composed of. And these must be positive integers. So the zones themselves have, as we saw, the list of geometries have different types, and so these have to be identified, or these are identified in the import command by the following, I guess, information. So that the B8 would relate to a cube, as it has 8 grid points. The 6 or W6 would refer to the wedge, whereas the 5 refers to the pyramid. The B7 was a degenerated cube, and then the tetrahedron would be a T4. And so, as we're saying, these are related to these zones. So whereas a typical then, file name that would be read by Flac would look as follows. As we were saying, we're just clarifying the file referring to, this starts with a G, so this is grid point number 1 with the location XYZ, all the way, runs as many as you like, but grid point 457 has this location. And it would go through that whole thing, and then it would also then start talking about, now marking here, this is a comment saying that this is where now we're going to have the zones. So this is zone, and it's a B8, so that means it's a cube, and it has now this is first identifying this is cube number 1, and then the location of its grid points, so on and so forth, and then lastly the groups. So groups, zones are grouped into C groups, and so these IDs refer to the IDs in these zones. And so the zones will then have a similar or a same material assigned to all of them. So we're saying here that this would almost be like a strata layer of granite type 1, and all this the layer is composed of all these zones. And you see similar for a different layer called the ore zone, and they have a different material assigned to them. So briefly, kind of going through the motion of this import, I'll look into a very simple example. It's not the focus of the comparisons that we're going to be looking into later, but this is just for kind of showing you the step-by-step. Just to comment, in our review page, we will have this as a separate example, short tutorial for only this case. But basically, in order for, or the process to go through this is when you have a 3D file in Midas, in order to share the information to Flac, we have to turn it into a text format, TXT format, with the information of the nodes and the elements. So in order to do that, these are the simple steps that you would take. In Midas, you would go under the Mesh tab to the box called Options, and then select from Table, Node Table, it would allow you to select which sets, and this obviously we would select all the sets and click OK to generate this table within the program with information about the element number and then the coordinate system XYZ. So we could just then simply select all, right click in Midas and do a copy paste to Excel, copying all the columns to Excel. And then from there in Excel, we would just verify that all the numbers have a, four significant figures, and then simply just save it as a tab delimited text file. And it would end up looking like this with information about the node ID and then the XYZ coordinates. So let's say that's the first file we save. That's going to be the information where the node, you know, locations are. So that would be the first component of this Fish Import.dat file. This is what it looks like, and the first aspect of it is going to be simply creating an array of 5 million by 5 million elements, and then calling this text file, in this case referred to as the nodes of the dam problem that we just saw, .txt. And then this basically loop is gonna just read through all the information, all the lines of information, extracting each one by one, and assigning basically just the ID and the XYZ information into basically a Flac3D file. So it's basically transferring that information and related to these four components: the ID and the XYZ location for each node until it gets to the end of the file, and then just save it into a format that Flac can read, which is in this case we're naming as Midas mesh import.flac3d. So we have to just repeat the same process now, but for the elements. And so in this case, again, we go to the same part of Midas under mesh, options, table, and now we select element table. And here we would refer to, or again, we select all the mesh sets to create the table. Once we create the table, again, we select all, copy and paste into Excel. However, here there is one modification we have to update within Excel, and that's related to column C. In the export process of Midas, the column right now has information about the material property assigned to each element. So this is how within Midas the program keeps track. And so here we see for this example that we have a list of 6 materials. However, even though we point this out, is that there are actually some materials that are assigned to more than one mesh set. They each still have to have their own ID number, as you can see here. So even though in Midas, we have named this, let's say, the material for the filter on the left side, there's also now a material for the filter on the right side. They have the same properties, but we see here that they are being identified by two different numbers and names. So Flac cannot take the information about the name and do anything with it, but what it can do is it just needs the number that identifies that material. So we just have to go and replace for each of the sets the name for the corresponding ID number. And once that's been updated, then now the file for column C can, once you finish updating all of, in this case, the six sets of materials, you can then just save it as a tab delimited, and this is the information that the program would have. So it would have the ID number of the element, the type of element, the material property assigned to it, and then information about the node IDs. So once that text file is created for the elements, this is the second component of the mesh import, that file, which is to read the information out of these elements. It calls that text file, and then we see here that this loop, what it's going to do is similar to what it did last time. It's going to go through the whole lines of the text file and save the information about the ID, and in this case now up to 8 node numbers or IDs of nodes, 8 being the maximum it can be. And the program will then go through this else if conditions and determine if it is a value at the 8th position of the text file, then this must be a cube, and hence it will assign a identifier as B8, and then it will go through the same process. If it stops at 7, if there stops at 4, or whichever, the whole process, it starts to assign the identifiers for the type of element that it is, so that it knows how to organize it. And then it just saves that into the same Flac3D file that we're creating now with the node information. And then the last part of the import fish routine is just creating an array and identifying what basically material property or ID, and hence zones or groups, are assigned to each of the zones. So it's basically grouping all the zones into respective, let's say, matching layers that are each going to have the same material ID assigned to them, and then it just saves all that information into the same Flac3D file. So in short, and we'll go through the example in a second, but in short, the first part is just basically take all the information about the nodes, take all the information about the elements, and then I'd go through and make sure that based on those IDs assigned to the elements are now known as zones, how to group them together. And in order to execute this example, we would just then open and create an additional .dat file, a very simple one, and just basically saying to call for this, import that file. And so that when you run them in Flac, for this example, we're not running an actual calculation. This is very much just about explaining the process of import, and it's something you can, we share as a separate simple exercise, but it was just in order to show the import process of it in Flac. From here, of course, the user would have to devise information or write the code about how to solve this model. However, like I said, we do have this full tutorial in Midas GTS NX that will be in a review page, so that you can go through the rest of the process in Midas, starting from scratch all the way to the end, and for this dam seepage analysis. Okay, so now that we've gone through the whole process of describing the import, let's now look at specific examples. The first one being, it's going to be a stress deformation analysis, a construction stage analysis of a bridge pier for a suspension bridge. We see here the starting terrain. It's irregular. We're seeing the isometric view, the top view, and the lateral view. So we see each of these different color layers represent a different material assigned to the problem, or to the model. Here's a little more detail now once the model has been, let's say, reached its final stage of construction. So there's the pier, the concrete pier, there's some footing, there's actually a fill here. So we will go through this construction process of excavating and then installing the fill and then the pier. And then we see here the designation to all the other materials, the names, I guess, we've given them. And more importantly, I guess, in this table, we see the information about the material properties assigned to each of the materials. So just to clarify that the export process of the mesh does not bring information about the materials. As we will see in this example, once the mesh has been brought into Flac, the user in Flac has to additionally assign, the material values to each of the zones. So this example is actually a construction stage analysis. The first stage will be of just initializing the stresses. We see here, you can see by the, even the shapes of, the meshes, that this is going to be an area that will be basically overlapping for a little bit, in the sense that elements will be removed and then reactivated later as a different material. So that's another key difference, is, as we'll see, this is going to affect our export process for this particular example. Midas can handle having multiple meshes in the same model, so long as they're not activated in this at the same time or in the same stages. So in this case, we're gonna follow a sequence of deactivating, these mesh sets and then later activating other mesh in the same location but are now related to the bridge. So this is possible in Midas, but this is not possible in Flac. And hence the mesh cannot be exported as it is. We'll see in a minute how we get around that problem. So the second stage of this analysis would be just the excavation of where the pier is going to be. This third stage is we'll be activating or installing a filling, a fill to support the eventual footing of the bridge. The fourth stage will be the construction of the footing. As we see, or we were referring to, this part is where there used to be other sets, meshes with, I guess, would have overlapped if they were activated together. But it's not a problem in Midas so long as they're, now activated in different times. Then the fifth stage would be the installation or activation of the bridge pier. And we notice there's a beam supporting the in between where this is where the location of the loads are going to be applied. So then the last stage is where we apply the asymmetric loads, and this will be the location XYZ. So X, in this arrow being in blue, these are global coordinate system, 500 tons. Y direction horizontal transversal would be 400 tons in the Y, and then the vertical load would be 200 tons. And they're all being applied to the beam in between the columns. To point out, this model in Midas has a count of almost 14,000 elements. Sorry, 140,000 elements. So it's actually more accurately 137,000 elements and about 68,000 nodes, and it took 12. Okay, so now we're going to go through the process of exporting the mesh. We see here the layers. We see that this is a construction stage analysis and that there is an overlap at this moment of two meshes. We'll see here part to be excavated and then also the footing. So this is not a problem in Midas so long as they're both not activated at the same time. And why we're doing construction stages. However, in Flac, that's an issue, and we're gonna have to do a workaround by moving the mesh set in a different position. So in order to prepare for Flac, we're gonna make now some or go through the steps in order for exporting. But as I'm saying, the pier, the structural elements, the footing, and the pier itself will be translated or moved to a different position so that the meshes don't overlap, and hence the information can be read by the program. So here I'm gonna go to translate the pier of the bridge as well as the footing, and I'm gonna do it in the vertical direction 100 meters. This is just an arbitrary decision to separate them enough in order for the meshes not to be in the same position. So there, I've just translated, and this is only for the purposes of exporting the mesh sets because of the construction stages. Had this been just a regular static analysis, as we will see in the second example, there's no need to do that. But this will be moved back into place once we're back in Flac, and so we'll point that out in the code. So here now, we see here then this is going to be the mesh set that will be excavated. That will be stage 1. But even though it has the same material as the surrounding soil, in order to prepare it, I do have to give it its own property material ID, just so that on the table so it's identified as its own thing. So to do that, I will make a copy and call it, a material property for this excavation. So I'll give it the same name as the mesh set. So I have added an extra material property to assign now for the set that's going to be excavated. Again, even though it has the same material as the surrounding layer, for the export process, each layer has to have its own material property ID. And hence why we've now created material property ID 11 for the set to be excavated. So we see here now, I mean, everything else is ready, so we can save it. We've prepared the model by moving the sets, also by assigning an additional property. So now we can get ready to export. I go now to mesh all the way to the end and go to table, node table, and I select all the mesh sets. I scroll down all the way down and I click OK. The program will take a minute, but it's going to generate. Now we see here the table, the first column being the node ID number, and then the rest being the coordinate system. So I'm going to select all and then right click copy, open Excel, and then paste. So here's just taking a second while I open Excel. And I just paste over the 4 columns. And so again, we have the ID number of the node and then the coordinate system XYZ. The middle column is not really carrying information that we care about at this point. What I do need to do though is make sure that all my number cases have the same number of decimal points. So here I'm updating the information to give it up to 6 decimal points for the coordinate system. And I'm going to save this file as a text file tabs delimited. So first I save it, save the Excel file just as a backup, but I am now going to save as, and this is the format that is going to be read by Flac. It would be .txt file under tabs delimited. So we now have the information about the node locations and in the system, the coordinate system. We'll open it here just to see. It's the same information as in the table, right? So the first tab related to the ID of the node and then the XYZ coordinate system for all the nodes in the model. And now we go back to the model and we will repeat the process now for the elements. So we go back to mesh, table, and this time we're going to generate an element table. And again, we select all the sets, mesh sets. This might take a little longer than the previous table just because it has more information. Okay, here we go. So now we see we have the information about the element ID and then properties and all the nodes. So I'm going to do the same, copy, and then open a new Excel file and paste. So I just go, right click, paste. And we see here again, we have the information about the element ID, the type of element. We see in this is type of element in the C column. We have the program has assigned the properties, and then all the other columns are the node numbers related to the element composed of those nodes. So we save this now as a element Excel file. Now we need to modify this file before it's able to be read by Flac, particularly column C, which is the information of the material property assigned. Now, Midas has generated the table with the ID number as well as the name of the material property that we created for each element, which is fine. But in order for Flac to read that, all it really needs is a ID number of the material itself. So we need to update all the material properties in this column to the respective data number. And so here I'm creating just I guess using the commands in Flac, such as replace all, is one way to easily go through this. So I would tell it like replace, the name of this column with just the ID number related to the material property. In this case, the matching ID number is 2. So I just tell it to replace all. And I will go through each of these until I get, and particularly in this example, all 11 material property IDs. So, I just skipped ahead and did it to, all the way to the last one. So here I'm replacing the name with just the number 11. And again, these are corresponding material property IDs for each of the mesh set layers. So now once this has been, done for, again, all 11, I skipped ahead just to save some time. Then the file is now ready to be saved as a text file for Flac. So now I can go to save, and I go to text file, delimited. And so it's been saved, and now if I go back to opening that text file, we'll see that we have the information about the nodes that represent each element. So we will now call in Flac the import.dat routine. So we see here the first part calls the text file and it saves into a Flac3D format. And then once I execute, it'll go through the same process and also import the element information we see there in the second part with the element text file. So here it's going through the routine and identifying the information in each of the two files, the node and the text file, and putting it in a format that can be read by Flac3D. Although we also have, for now we're running first the import.dat files. In this part, that last modification, that's what we were doing. We were letting the program go through and find the IDs related to the zone groups and assign them properly. So now it's ready and we can see what that looks like in Flac. I'm gonna go to here to show the zones. I'll show you now in the program what we see here, this first part. So we haven't run analysis yet. We just ran the routine, Flac routine for importing the meshes. And we see here that they're the matching IDs that we updated corresponding to each material for each set. Basically, each set has its own ID of the material. And so now we can go through the process of import it into Flac. Then we'll see in a second that it's easy for then in Flac to just tell it that these new zones have to be moved back, back to this location at a certain stage. So they can also do the construction stage setup, but just that there will be a command or part of the command in the stage of the activation of the pier is that these sets have to move down before they're activated. But let's now look at how we do this example through the motions of everything from exporting the tables to importing it and running it in Flac. So we saw that we ran it in Flac, and these are now the results for the stages. So the first stage we see, being the initial stress stage, everything is activated here. All the zones are shown, well, here shown in color by Flac, and here on the side is just a annotation related to the IDs given to these materials in Midas that was basically read and assigned matchingly in Flac. So right now we have these materials activated. We notice that basically there's no information for the footing, which is like the would be zone property 1, or as well as what would be for the pier, which would be number 8. So we see that those zones are not activated here yet. We've now gone through the first stage of excavation, so we see now we have deactivated zone 11 related to the first excavation in the other, Midas model. And now we get to the stages where, the footing has been activated, zones, what would be zone 1, and then eventually as well the pier, which is zone 8. So in the program, now we're looking at not the import but the calculation fish routine. So the first thing that this does is it calls for the dat file that is for importing the 3D meshes that we just covered, and then it goes into starting to assign what would be everything that the model needs, the gravity load, the loads that would be assigned in the x and the y and then in the c direction, as well as applying boundary conditions for the fixing the displacements and all the directions, and then starting to would be assign the groups and the materials for each stage. So this now is going through stage 1, assigning the material properties to each group or zone group. And then this is just to initiate the parameters. Stage 2 is where we remove, or in this case, as they're saying here, deletes group 11, is remove the excavation. Stage 3 is a field construction, so you just activate, group 3. Stage 4 was the construction of the footing, and so here we again assign the materials, and you call group 8. And as we said, this command in particular, we see here that it's initial position at -100. So this is where it calls in to correct that mesh that was imported is in the location, the original location now, or in the correct location. So it's bringing it back 100 meters. And then assign the materials, and these are just related to the output. We want graphs to track the displacements in X, Y, Z directions. And then we do construction stage 5, which is the activation of the pier. And again, these are just tracking the results at different points on the pier. So point C at the top of the crossbar, point B at the bottom of the crossbar, etc. And then lastly, this last stage is the application of the loads in the different directions. So the vertical X and the YC. And then to point out, these last 3 boxes here in different colors are what we call the solver ratio. And this is what the program Flac uses to determine its reach the solution. And it's a ratio of the maximum unbalanced forces to the total applied forces in the model. The default, as shown here, is 1 to the -5. However, we are going to add an additional condition for solving a more strict condition, which would be also additionally to this one, 1 to the -7, and then beyond that to add an additional 400 time steps or calculation steps once it's reached the solution at 1 to the at this criteria. And we'll see that it's very important in the results in a minute. So here are the results for Midas. Displacements in the X direction with deformation. So we see here from the different views, but we see we're getting around 17 centimeters maximum displacement, and it's looking like in the X direction it's at the top of the pier. Looking at the Flac results, here we're corresponding to graphing displacements in the X direction at 3 different points on the pier. As we had said before, the red line is displacement at the very base, the green line is displacement in the middle, and then the blue line would be displacement at the top. So we see that by the default solver ratio criteria, the program stops here, and even looking at displacement graphs or on the model, it looks, even in the range of values, it looks like it has stopped prematurely. If anything, the displacement was still seem to be growing in where the direction where the load is applied. And so we don't really know, what the final values would be. We now look at the second criteria that we established, and we see that this is now starting to look more as we would expect. And we see now that it's the displacement at the top of the pier that's really starting to grow, and it's starting to get to a range that's more of what we had expected. In this case, it's still at around 11 centimeters. But it seems to still be growing. So if we look at the final criteria, the third criteria, where we added an additional 400,000 steps, we see now that this graph has been able to stabilize at reach its peak, and the results now look as more expected, and now we're in the range of 14 centimeter displacement. But more importantly, looking at the graphs as stable. or flat. What I mean, they've flattened out. Similarly, for the results in the y direction, we see here, which would be in the global coordinate system to the right. So we see the deformation, of course, and the pier twisting, and we're getting around 5 centimeters in this case displacement. Comparing that to the results in FLAC, again by the default criteria, we see that the graph is still would be still showing there's missing information, more displacements to come. If we look at the second criteria, again, the top of the pier is the blue line. It's starting to show that that's where the majority of the deformations or displacements will happen as expected. And it has curved off. It seems to be here that at least these have all three flattened out. So it could potentially be that for, in this example, this criteria would have been sufficient. Again, if we were just to look at it, at third graph for the criteria, then it does kind of drop a little bit, but they eventually do all flatten out at around the same, around 4 centimeters displacement. And the results look similar to Midas. And then lastly, the vertical load applied directly here in the pier. We're seeing here about 4 centimeters displacement, maximum displacement, and in red, and then about what would be 10 centimeters in the blue. So positive being up and negative being down. So it's about 10 centimeters would be like here. So we see now in FLAC for the first criteria, again, for all three locations, the graph is showing that the displacements are, going down, but they're still not clear. I mean, it's still developing. Looking at the second criteria, we can see that this is where the previous had stopped. These have, again, flattened out with the most displacement happening in the bottom, in this case, of the pier, as expected. And then the last criteria, there's not that much new information. In this, again, for this example, it seems like this previous criteria would have sufficed to give us accuracy and accurate enough results. And we're seeing a maximum displacement in the down direction of about 8 centimeters, close to the 10 that we saw for Midas. So the results are pretty similar, but just very much wanting to point out that it's very easy to have missed the results by just leaving the program on the default convergence criteria, and why it was so important to add these additional extra solver ratio convergence criteria. So lastly, we'll look at an example for seepage. We had originally thought about doing a dam example, but we thought it would be easier just to use one of a very common textbook problem, as you could call it. It's actually one of the verification models that Midas has. And so this is just basically a permeable rectangle. We have a water head of 15 meters on the left and a water head of 10 meters on the right, and we know the dimensions. So using this equation, we can estimate what the quantity flow should be across the model, giving what would be permeability function data assigned to the material shown here. So it's a very simple, actually in Midas, we ran it as a 2D model, and it took 1 minute. And in order to export it to Flac3D, we just had to extrude a unit thickness. We extruded it by 1 meter and created basically a 3D set. And in Midas, you can actually just rotate any mesh sets about an axis, 90 degrees if you wanted to, because we did go from 2D to 3D, and in 2D the vertical direction is Y, but of course in 3D the vertical direction is C. So you can either do it in Midas before exporting it, or you can just keep track, making sure that you're correctly just flipping the information about the node location coordinate system of Y to C and C to Y. And so either or, you can just basically make sure that you're now going into a 3D environment, that your vertical direction, the C, is related to the vertical direction of the model that we ran in Midas as a 2D example. So the import process would be the same, and here just now running into the calculation file, we see the first thing is to call the import of the mesh set, and then we go through assigning now the fluid properties. have to point out in Flac, the user gave this value for the bulk modulus, what would be the fluid compression modulus, and it's very high, unrealistically high, and we'll clarify why once we see the results. But this is just basically done as a cheat to try to reduce the calculation speed and make it run in a more reasonable time. But it won't affect the result, the quality of, or the final output of the result itself. So you assign the materials, and then you just assign the boundary conditions, and then just define what would be the calculation flow. As we said, in Flac, you manually input the equation that you want to use for your calculations, and you set up your own loops. And so here we're also now using the same equation, and then for the output, what we want is we're actually going to compare doing the calculated by Flac, and then we're going to add this manual equation. I would call it in here theory, as a comparison to the output of the graph. And then we're going to keep track of the history of the output and by the calculation done by Flac, and then as the hand calculation theory, and then just save the results. Point out that this model took 77 minutes to run in Flac, whereas it only took 1 minute to run in Midas. Here's the output in Midas. We see the distribution of the pore stress as we expect, 15 on one side, 10 on the other, and here's the water line. And then looking here at the flow, the seepage flow with vectors, we can use a function in Midas called flow quantity, and I can select all the nodes on my left side face, and it'll let me estimate the quantity, the flow quantity. In this case, it's calculating about 0.627 meters cubed per day. Whereas by the hand calculation, given the dimensions that we have, the head and 15 on one side, 10 on the other, and then the length of our model being 100, the hand calculation estimates it to be around 0.625 meter cubes per day. So it's very, very similar. And then here are the results for the same thing now in Flac. We see here the two graphs, the red graph being the output result that we just solved manually, the hand calculation, and the green line being the result done by Flac. And we see that eventually it does reach the same result. However, we do see that this curve takes time steps to eventually get there. And this is us giving it a high value for the bulk modulus. Had we used a more realistic bulk modulus, this line would have had a different curve and it would have taken longer to reach the same point. So this is why we added that other value, just to make it run or reach the final result faster. So in conclusion, what we've shown today is that Flac does have a command that allows it to import volumetric meshes. I know, but it has to be in a certain structure. There are important differences between the two that we pointed out between the two softwares, GTS NX and Flac. One uses elements, the other zones, and then the how to input commands or instructions into the models, as well as the generated stages, all that. So we saw those differences. Using the Fish subroutine, we can easily import meshes now from GTS NX. We saw the proper format and the proper workflow to make all the files that we need, basically the text files, in order for the Fish routine to be able to import. And then we showed how to, or we showed once this, mesh was imported into Flac, we ran it for the stress, deformation, and seepage for 2 examples. In Flac, we also pointed out that we must also generate a calculation file, and not just the import file. Like once the mesh is imported separately, you have to create a calculation file. However, that's points out that any kind of analysis can be made in Flac because you code it yourself. We saw that the results match between Midas GTS NX and Flac3D for these examples. We also showed that the calculation time for Midas is significantly lower than for Flac. And actually, I'll point that out again in a second. I might not have been clear in the first example, the time difference, but in the second, we saw a difference almost of an hour. And the last point is that because you have to code in Flac3D, it does require you to the learning curve is much higher. There's required a lot more training and skill in order to complete a model that was, similarly done in Midas GTS NX. So just to point out this last point, as we had said, the calculation time in Midas for this problem was 1 minute, whereas in Flac it was 77 minutes. And for this example, the calculation time, I missed to point this out, the calculation time in Flac was 466 minutes, whereas in Midas it took 12 minutes. So this is the conclusion. Now we pass the part to the questions with our speaker, and I would like to point out that our review page will have all the material from today's session, and you can see it here as well as the recording to the session. And so we encourage you to go to our page and see the material. There's also the demo version of the software. If you have any questions, you can contact me directly at this email. Thank you for your time.